Okay, I'd like to introduce for you our next keynote presentation. Like to introduce from FADU Technologies, Ji-Heo Lee, who is CEO and co-founder. He's a former partner at Bain & Company, a successful serial entrepreneur, involved in multiple businesses in technology, telecom, and energy. As CEO, he's established FADU as a fabless semiconductor innovator, uniting exceptional industry talent, creating a revolution in data center and storage for the next generation of computing and architecture. I'd also like to introduce with him is Ross Stenford, who is a member of Meta's storage hardware team. He's been someone presenting at FMS for many, many years now, and we welcome him back. He works very closely now at Meta with our standards organizations for our industry, including NVM Express, SNIA, and the Open Compute Project. He has extensive experience in ASIC design and an appreciation for the challenges facing SSD providers and delivering performance and quality of service within a shrinking power envelope. Ross is an inventor with 40 patents, so I'd like to welcome FADU.
Hi, thank you for joining the keynote. Actually, I'm very happy to be here after 3 years of absence from the FMS 2019. And, today, I'm very honored to be with Ross Stenford from Meta. He's a very respected engineer, and he's really contributing a lot in OCP and other standards for SSD. So today, Ross will share his perspective about enterprise SSD as a customer, and then I will share my perspective as a supplier of SSD. Then probably you can catch what is going on in this industry. So first of all, I would like to introduce Ross. Yeah, please welcome Ross.
Thank you, Gio.
Yeah.
It's great to be here today. Let's see here. So today I have a few perspectives on hyperscale and storage. I really appreciate your time today. And with that, I have my favorite slide from the lawyers. I hope you all enjoy it, and I hope that you have some better slides to look at after this. So let's start off with form factors and challenges. M.2s, they have a bunch of challenges. They're power limited. The connector is very SI challenged, especially when you go to like PCI 5.0, insufficient NAND placements, serviceability, security. Can you tell we're in a world of hurt? With that, what does the market really need? We need something that's PCI 5.0 and beyond. Scalable, power, performance, thermal, density in 1OU, serviceability, security. Fortunately, there is a solution for us today. It is E1S. The connector is designed for PCI 5.0 and beyond. It has scalable power, performance, thermal, density in 1OU. In addition to that, it's serviceable, it has security, and oftentimes I hear people say, you know, Ross, that's your opinion. And you know what? That is a perfectly valid statement. That's my opinion. But let's look at it from another perspective. Let's look at the trend focus numbers here for share of data center enterprise PCI units. 2021, 2.4% of the market. Not too impressive, I have to say. That being said, project out 2026. Over 50% of the units are expected to be E1S. There's only one way that happens, and that is it meets market needs. That is the only thing that could drive that level of demand that fast. With that, let's talk about thermals. Let's start off with, you see a couple boxes on the right here. These, the one on the top holds over 700 terabytes in 4OU. The one below it, over 500 terabytes in 4OU with 25 millimeter E1S drives. And you're like, why are we talking about thermals? Well, unfortunately, buildings have limitations with power and airflow, and those are very precious resources. and you really don't want to run out of either one of those. That's not a good thing. So I want to show you a graph here. On the bottom, you see the width of the E1S. On the right side, you see the power needed. And then there's this important black line. It says 0.145 CFM per watt. This line is our thermal limits that we need to meet to ensure that we don't run out of power, don't run out of airflow. This line is based on these boxes you see on the right here. And what you see is with 25 millimeter, we are able to achieve 25 watts and meet those design requirements. Now, before I get misquoted, does this mean that 15 millimeter cannot do 25 watts? No, it does not mean that. What it means is you can do that, but it needs more airflow. But this also points out here the great benefits of E1S. Everybody has different design constraints. And E1S allows, with the same PCB, the same firmware, you can get heat sinks based on your design needs. Whether that's 25, whether it's 15, whether it's 9.5, you can pick your E1S drive and then pick the thermal solution based on your design constraints. Let's continue on. Let's talk about SSDs and specs and challenges. So customer requirements are confidential. This creates a whole bunch of problems. Standards have many optional features. What do I support? What are the real customer requirements? And limited access to competition. You know, I have my top 3 friends. I give them my spec. You know, who else gets a spec? How does the industry know what to build? Everything becomes, you know, customer-supplier relationship. In addition to that, that leads to a highly fragmented market with lots of SKUs. Many customers ask for similar but different features. SSD suppliers have finite resources. No matter how big the firmware team is, it's not going to be big enough. In addition to that, you have third-party test providers who don't know what customers require, so they write test cases, but are they what matters or not? I don't know. What does all this result in? It results in product introductory delays, lower quality, difficult product feature decisions. What's that mean? That means customers are unhappy, suppliers are unhappy, everybody's stressed and unhappy. Fortunately, there is a solution to this problem. The OCP Data Center NVMe SSD spec. You can pull this off of the OCP contribution website today. What's the purpose of the spec? It's to align the hyperscaler and OEMs and the SSD vendors to common features resulting in focused resources, improved speed, improved quality results. It provides everything you need to build a hyperscale OEM SSD, whether that covers NVMe Express, PCI Express, security, everything you need. In addition to that, it not only has that, but has shared learnings between many people on deployments at scale and problems. Let me take an example. There are 10,000 drives running in production, live traffic. There's a spike on one machine, one time a day. Every day it's a different machine, different drive. How do you debug that at scale? A very challenging problem. Well, in the spec, there's a latency monitoring feature. This will enable a couple things. First of all, it'll help you identify, number one, is this the drive or not? If it's not the drive, guess what? Hyperscaler needs to go figure out what's going on in their system. We're not going to bother the drive maker. If it is the drive, it has hooks that will enable you to debug this at scale in production. Very challenging problem. Now, in addition to that, since we have an open spec, guess what? We can have open source tooling. So here you see the NVMe CLI plugin with OCP. It is on GitHub today. You can pull it down, and know what? You can even use that tooling today to control the latency monitoring I just described. Some history about the spec. This all started out with Meta and Microsoft in 2019, realizing we need to stop arm wrestling with all our suppliers to get drives and collaborate and help them and make things better for everybody. In 2020, Meta and Microsoft contributed the NVMe Cloud SSD 1.0 spec, which is the first public industry spec of this type. In 2021, HPE and Dell EMC also joined the effort, and we had the Data Center NVMe SSD 2.0 spec. And what's this result in? It results in more features, better quality, and faster. Now, those are very unique characteristics. You can always get one of these things. It's really hard to get two. But it's very unusual to get all three with features, better quality, and faster. Getting all three of these is a huge win. So in the end, this is an industry collaboration win for everybody. Now, let's switch topics to another topic here. Let's talk about write amplification. Early 90s, what did we do? We over-provisioned. And that's great, but now I paid for a bunch of capacity that is not usable. Then 2007, 2008, guess what? Trim, deallocate. Host can provide LBA hints. That's great. Now we're on the next stage of the journey here, 2022. And the next stage is the host can provide media placement hits. This is called flexible data placement. It's very, very interesting. This comes out of innovation, out of two hyperscalers and collaborating together. The goals of FTP is to provide high-level media hints. It's backwards compatible. It's designed to make the drives you have today work better. Some of the benefits are it significantly improves write amplification, it reduces device wear, and improves performance and QoS. Let me walk you through a simple example here. Let's take disaggregated storage. We have three applications. They're all talking to the same drive. The data is mixed, and all the workloads of these three applications are completely different. The device performance is unstable. It never reaches steady state, as these are different workloads. So you keep on over-provisioning the drive for a long time, and eventually the drive, it becomes stable. And you go ship it. That is your standard disaggregated storage model today. So let me walk you through an example here. And so as the first row across you see is without FTP. So you see these blocks. These are super blocks. If you want me to define a super block, it's a stripe of blocks across the NAND lanes. You may have XOR over this for recovery or some other type of additional recovery mechanism. And so you have three super blocks here. And application A, B, and C, they write their data into these super blocks. And then application A deallocates all this data. We say, great, that's a win. We are so much better. But now when you go to the right, you see the data distributed across the media. You see all those green blocks? Those are all areas that data has been invalidated. We need to go garbage collect that. What that means is we garbage collect that, and we get a WAF of 3. Now, how does this change with FTP? Let's go to the bottom row here. So once again, application A, B, and C, they write their data to the media. However, application A goes to one super block. Application B goes to the next super block. Application C, it goes to the next super block. You see how the data is distributed across these super blocks. Now, application A deallocates all its data. Guess what? That's all in one super block. That means I can go erase that super block. And that also means now the data for application 2 and application 3, it doesn't need to be moved around on the back end of the drive. That means I have a WAF of 1. And this is a significant improvement. I just reduced the drive wear by 3x in this example here. I should say I don't have time to do justice to this topic, but tomorrow there is an NVIDIA Express talk at 9:45 with Google and Meta, and I will be there, and we are going to talk about this in depth if you want more details. But it's a very interesting and challenging problem. I'm sorry I don't have time to give you all the particulars around it, but it's very exciting. So with that, I want to thank Gio for your time today and inviting me, and hand it off to you. So
Yeah,
thank you very much.
Thank you. Thank you, Ross. So it's probably my turn to answer his question. So let's start from the very fundamental question. Why we are using NAND? In my view, NAND is one of the worst semiconductor ever. It's very slow. It's well broken, easily worn out. But it has a really strong strength. It's a really important strength, the price, right? It's a very, very, very cheap. That overwhelms all other problems. That's why we are using NAND. Now data is exploding, and the data center wants more SSD, more and more. They have the two demands. They want to have the more reliability. They also would like to have the faster performance. That two challenges quite problem because NAND company is trying hard to compromise quality and price. So even though the NAND price is going down, quality is also going worse. So as you see, the P cycle is going worse every year. At the same time, they do like to boost the performance throughout the innovation of the PCI standard. So that is a big challenge. Someone needs to take care of that. Who is doing that? The controller company. Now the controller need to have the more work than before. That creates another problem, the power and heat. So in 2019, when I made a keynote, I tried to make some wake-up call. I would like to say that the industry needs to more focus on power when you need to design the SSD. So in my analogy, suddenly customer asking much faster car. What industry had been doing is just developing the bigger engine. But the problem is engine is too big now. You cannot operate properly. So you need to change the way to design the controller and the SSD. That's what I tried to say at the time. Today, I have some mixed feeling. First of all, I'm happy I was not wrong. But at the same time, I'm sad because our customers are struggling. So let's kind of see about the detail. So that is kind of what Ross shared. Actually, there is a clear limitation in heat, even in a modern data center server system. Without heat sink, SSD allowed to have just single-digit watt of power. In Gen 3 M.2, SSD will have the 8.5 watt max. Probably the realistically is 8 watt. To deliver 3.5 gigabyte per sec, NAND itself should consume more than 4.5 watt. And then PCB, PMIC, DRAM will consume 1 watt. Then what remained? SSD controller should have just less than 3 watt. Most of SSD fail to deliver. That's why M.2 is struggling. That's why our customer asking the new form factor, such as U1.S. U1.S Gen 3 would be fine because power is somewhat increased to 10 watt or 12 watt. But the problem continues. In PCI Gen 4, we need to deliver 2x performance. Then NAND needs 7 watt. Then controller power just 5 watt, which means kind of just 20% upside for the power consumption. In Gen 5, we need to deliver 2x performance again. Then NAND need to suck 11 watt. Then controller need to have the 7 watt. The key issue is whether we can deliver appropriate full performance of Gen 5 with less than 7 watt power frame. That is most critical issue, and that's where many companies are missing. So that's why we are here. So in the case of the Gen 3, we announced in 2018, actually our Gen 3 controller was good. That consumed just 1.9 watt at that time. That was first SSD delivered full performance in M.2 form factor without any heat sink. At the same time, that was first SSD delivering higher than 100K IOPS. And then one more thing is kind of our customers love it. So now I'm happy to announce that we are in a full mass production of the Gen 3, Gen 4. Till last year, I has been asked, you need to prove it. But now I can say we proved it. So we are kind of proving ourselves throughout our superior product. So today, I'm very happy to announce our Gen 5 SSD. So the customer sample of SSD will be delivered early next year. In this SSD, our controller will consume the 6 watt. It will be the lowest Gen 5 controller ever. And it will deliver higher than 200K IOPS. It will be the first SSD which deliver 200K IOPS for the data center purposes. So as I said, we have been focusing on solving the power problem. But as I said, delivering the performance is quite easy. The problem is you need to control the power. So after solving the power problem, other thing is quite easy. So we don't really forget what our customer needs. So one important metric in data center is not really sequential read, sequential write. The latency Q is one of the most important metric. In our Gen 4 SSD in the market now, our latency is much more consistent than any existing SSDs. The reason why is because we can control power much more efficiently than our competitors. So many people just check the sequential read is how many sequential write, random read, random write. That is not important in data center. Two most important questions you need to ask to SSD vendor is, one, what is your power consumption in maximum performance? Number two, what is your latency QoS? That is the most critical question. If you don't solve that issue, there is no SSD appropriately. That's what I would like to say. So let's move on to the kind of the OCP. We always believe that we need to deliver the product that our customer want. So we would like to solve the problem that our customer have. That's why the OCP there. OCP is a very systematic approach to set the standard for customers. So throughout the OCP, SS developers like us can easily understand what customer want, and we can easily deliver the solution. So that's why we love the OCP a lot. We have been a strong supporter of OCP and trying hard to implement whatever the OCP asked. So our Gen 3 SSD, for example, the Ross mentioned about the latency monitoring feature is already included in our first generation SSD. So you can see the demo, live demo in our booth, so please visit there. And all other kind of features we love to execute because we know OCP is great spec. And the more important thing is the GNS FDP. As I said earlier, the WAF is quite important question for the customer. They would like to have the more reliability. So they try to find out the right spec. Now we are happy to see the GNS and FDP. So we executed the FDP now. So in our Gen 5, it will be the first SS in the market, which will be perfectly execute the FDP function. In this industry, I believe that the PCI Gen 5 is really important, not because it's fast, but because it's matured spec first time. In Gen 3 and Gen 4, it's not fully matured, so some companies are asking very different features, so there is a lot of confusions, a lot of ambiguity. So we have been struggling to figure out what is the right spec to deliver. But from PCI Gen 5 and the OCP 2.0, now we are seeing what is a really matured spec, what is really important for customers. So I believe PCI Gen 5 is a really important product in this industry, and I'm very happy to say our Gen 5 SSD will be the best SSD ever. That's what we are doing now, but we don't want to stop here. We would like to see the future. So yes, CXL. I know that many people talking about the CXL now, but before discussing the CXL, we need to answer two questions. Number one, can DRAM continue the Moore's law? I heard a lot about the complaints regarding the DDR5 price. The Moore's law is struggling to implement it in the DRAM. Then how can we get there? Probably one idea that I have is probably they can learn from the NAND industry. As I said earlier, NAND industry try to compromise quality and the price. So that's how we get the benefit of the low price of the NAND. If DRAM follow that kind of way, there will be another way to extend the Moore's law. In that case, probably there will be some sacrification of the DRAM, but it's a really good fit with the CXL because there is a controller. I believe controller will be much more important in CXL era. That's why we are here. Number two, DRAM is not enough. We need to have another NVM. But what option do we have? As you know, the Optane is gone. Do you see any other options? We still believe in NAND. There is some possibilities. I know there is a lot of doubt, but combining with the DRAM cache and the controller, I think that we can solve the problem. That's how we managed this company for a long time, and that's how we proved ourselves. So I will show probably about the CXL NAND in next year. So that's how I explain about what you have done and what you need to focus on, and that we will show. So I would like to close the presentation with one quote that will explain the FADU in a great way. So thank you very much. It's a problem. Yeah, thank you.